Okay, so today will be boring because I have to recall a few things about the root systems of simple algebras and various things, but since the audience is well acquainted with the subject, it will be very fast. So Lorenzo is not agreeing fully with this statement, but I was teaching the class, so you have no hopes. I know everything that we've done. So let's settle our hypothesis. So G is a connected, simply connected Lie group, complex Lie group. Okay. And then G is the corresponding Lie algebra. I recall that is the tangent space of the identity. I know that maybe you don't know this. Do you know? Is the tangent space sort of? Is that? Why it is important that G is simply connected? It's very important, but maybe we don't need it right now. So then we have some maps we really care about that we should know well, but let's. So there is the exponential map that goes from G to G. Now this is. Let us assume furtherly that G is in some GLV. Okay, assume that is a matrix group. This is not a severe assumption because from just a second we will talk about simple groups and simple algebras. In this case, is always true. So I'm saying that this restriction is not so fundamental because then we're interested only in those groups. If we have such a restriction, we can write the exponential morphism in an easy way, and which is to a matrix X here, we associate 1 plus X squared, and so on. Okay? You could define it even in general without this description, but we don't need the general definition. So this is now of course, there is a problem. So in this definition, there is something that should be checked. First of all, is that so this stays in some endomorphism or some vector space, and this sits into some automorphism of the same vector space, right? So it is true that this. Let me write a small remark. So it is true that if you go from the endomorphism of V to the automorphism of V, like this, this is well defined, in the sense that what you get here, it is an automorphism. You should check a convergence, because there is some issues of convergence, which are not, they're not terrible, but they have to be checked. But this, so if you look at this map, it's well defined. Okay. So if you write like this is an infinite sum, right? You should check this as a meaning. No, you're not happy with this.
Shouldn't be there factorial?
Yeah, the factorial. Okay. Yes. Sure. I forgot. It doesn't matter. It's the. So this is the exponential. This element is invertible. Its inverse is where you put the minus x here. You can check it's invertible. Now the problem is that if you define it like this is well defined because it's the restriction. But you have also to check that it is landing into G, right? Because it's not immediate that it's going to G. It's going to the automorphism of V. So this is part of the Lie theory. Means something that should be checked, but it is part of the theory. Now there is this. He's clearly thinking, the way he's writing, he's thinking about the matrix group, even if it doesn't say so, because he defines the exponential, he defines the adjoint morphism using the terminology for matrices. So let me. This definition, I don't know, is. No, I think it's right anyway. Okay, so this is the exponential. And then we are under the assumption that the exponential is surjective, which is not always true, but we assume this. And then we define big AD and small AD. So these are important morphisms. So the adjoint map goes from the group and gives an endomorphism of G. So takes an element X and associates the morphism taking the element psi to D to the T. Let's explain the term because it's not clear at all what this is. He writes like this, but let's write differently because we want to understand what is this, right? So maybe you already see what it is, this, right? Do you see what it is? This morphism written in this strange way. So it's very simple. He likes to write it complicated. So psi goes where? Goes to. So here we have. So it is. The exponential is 1 plus psi t plus psi over 2t squared and so on, right? This is square. This is what it is, right? Now if we apply the conjugation by x, we get 1 because conjugation of 1 is right? And then you have plus, and then you have x minus 1 psi x t, and then you have something which we don't care, t squared, right? And so on. Because remember that we're taking the derivative with respect to t, right? T is a number. T is a number variable. This is a matrix. So we're taking the derivative at each entry of the matrix. I'm sorry, I'm explaining things because I want them to be clear. Maybe it's too obvious. I don't know. If it is too obvious, it's not the problem.
It's not so obvious. It's not so obvious.
It's not so, yeah, the thing is that this is something trivial that rarely the authors say. So this is equal to what? To 1, the derivative is 0. Then the derivative here is 1, and then you take t equals 0, so this is x minus 1 psi x. And then this is 0, because this will be 2t, and when t is 0 is 0. So basically is the adjoint of x, this what he calls this, he writes like this, adjoint x of psi, okay? He writes like this. So the adjoint of x of psi is equal to x at psi x minus 1 for G matrix group, which is the only case that we will study. So this is the general, right? If you know the exponential, define the generally, then you can define big AD generally. But if you are content to stay in matrix groups, then the exponential is really the exponential of the matrix, and the adjoint is the conjugation. I think it's better to see it this way because it's very concrete. I don't see why we should get things complicated artificially. Now, so this is big AD. Now introduces also small AD. This is a representation. Big AD is important as a representation. So this is called this adjoint representation of the group. And this AD is the adjoint representation of G. as we know from the theory of classification of simple algebras, the adjoint representation of the algebra plays a key role, and we will see a small review. But for the moment, let me recall that so AD goes from G to the endomorphisms of G and takes an element psi, and what he writes AD psi is a map taking what he uses. I'm sorry, he calls this eta. Let's call it what. So psi is taken to AD eta psi, and is the bracket eta psi. This is the definition, okay? And one can show that the adjoint.
It's just the differential of that.
Yes, it's the differential. So the adjoint, the little AD, is differential of big AD, and so let us see. On the top of my head, if I try and make a disaster. No, I made a mistake. Here the adjoint you want x minus 1 first. So if we try. So no. Let me do it myself. No, don't do it, because I know you know it, but it's not fair. So, if we know the exponential is surjective, I think it's pretty easy to show this. So we're looking at the group element x, say, as 1 plus. Okay, so what we do. What do we do to prove this? Stephen, don't look at me, because it's always more difficult to do it when you are at the board. And this is going to be on YouTube.
Not looking.
So I'm embarrassing myself if I don't produce a proof of this. So what do we have to do? We have to take a differential of this. But notice that the differential will go from this object to this object. So we need to give a variation. You know what is differential, right? You need to take a curve on starting from x. So actually no, start from the identity, because this is the differential in the identity of this, right? Because see, you take a differential DAD, will go from the tangent space to the identity, which is G, to the tangent space, the identity on the. Sorry, this is the automorphism. I apologize. The tangent space of the automorphism of G, which is the endomorphism of G, right? Okay, so this is. You remember, if you have a morphism of manifolds, if you take the differential, you go to the tangent space. So the tangent space of G. So in order to see where a tangent vector is going, you need to take integral curve, pass into that, and see where it is going. You don't look happy. You're happy? Yes, okay.
Sorry, why the tangent space to the automorphism are the endomorphism?
That's a very simple thing, because remember, let's see it in coordinates, okay, because it's the same. So if you fix basis here, it's finite dimensional, of course. So the automorphism will be some GLN, right? Now GLN sits inside the matrices, right? The n matrices, which is actually a vector space, so it will become n squared, right? As an open set, because it's the terminal condition. So when you take the tangent to an open, right, this is coinciding with the vector space. Is this reason, right? Okay, so let us look at the small calculation that AD is the differential at the identity. So we should take d dt 0 of AD 1 plus epsilon, we call it, what did we call it? Eta. So we are taking we're taking an integral curve passing through the identity. I'm sorry, because this epsilon is the, no, sorry, I mean t, I decided to take. Let's call it epsilon, because I don't want it to confuse it with the other, okay? So I'm taking a an integral curve plus O the epsilon squared, okay? Then we don't care about this O, because this is going to be to 0, right, when we take the derivative. So this is d dt 0 of 1 plus, no, we take, so when we're taking the inverse of this is, will be 1 minus epsilon eta plus something that is depending on epsilon squared, psi, 1 plus, it's coming psi eta. Why did I do this? There is a mistake here because, right? I think there is a mistake because the sign comes different. Okay, let's see. So this is, so if we take only determine, because this determine the degree 1 of epsilon is the only term we care about, right? Because determine epsilon squared, when you take the derivative with respect to epsilon, will go away. So we have, and then the constant 1 will go away. We get minus eta psi plus psi eta, which is exactly psi eta, the bracket in the matrices, which is what we wanted, right? Because we are embedding our Lie algebra inside the matrices. So this is the bracket. I think there is a typo in the book because he writes like this, and instead the psi should go before. If you decide to have the minus 1 here, I mean, if you want the minus 1 here, the psi can, if we want there, it depends on the choice. Whatever. So we made this little calculation. So Stephen, is the calculation you were thinking about?
Yes.
Okay. No, maybe there was some smarter way,
No,
which I don't know.
I would have written it slightly different, but it doesn't matter.
You would have written it, but
You just take a one parameter subgroup, right?
absolutely, yes,
So yeah,
yes, it's the same. It's one parameter subgroup. I didn't call it one parameter subgroup, but this is what it is. It's an integral curve passing through the point, the identity.
Yes.
So if you come to my course on the groups, we will see all of this. More in detail, of course. Okay, so now let us go ahead. So we introduce small d, big and d, and then there is the dual of these. Let me just, do we need the duals now? We need the dual later, but okay, I may as well write something now. So if we don't need it for today, and I don't know when we will need it actually, but there is this AD star, okay, which are the dual. So of course there is G star, and we know from our discussion on the Poisson geometry that G star doesn't come with a so okay, I don't want to see because I will talk again about Poisson geometry, but not now. Let me just write what I mean. So G star is the dual because there is, you remember this talk we had about the Poisson geometry, the Lie by algebra structure. We said many things, but we don't need them today. So we will talk next time with more detail because it's not useful that we bring all this thing again now and no. But certainly we can define this, the AD star. So what is going? Okay, I hate him when he does like this. So I want to define this where L is an element of G star. Okay, no, right. So X is in the group, but now this adjoint star will be going, so this AD star will be going from the group I have to define it yet. What is the problem? So it's going to the dual. So this is, so this will be an element of the dual. So we'll take an element of G and associate L. So this is a pairing. So this thing is a pairing, right? You've not seen this before. So L psi is L psi. So this is the natural pairing between G star and G. An element of the dual, an element of the vector space, you associate the dual evaluated on that. So this is L evaluated at AD X psi. This is just the definition of AD star. It's not that saying anything smart, it's just the definition. And similarly, one defines the little AD star totally the same way. Okay, we will leave them aside and use later. Okay, so now I feel happy. So we have introduced a basic language for general Lie algebras and Lie groups. We have introduced a little restriction that these are matrix groups, but right now we're going to consider a far more restrictive hypothesis. We are assuming that these are actually simple. When I say simple, automatically there will be matrix groups. So our previous hypothesis is already okay. So further we assume G is simple, the Lie algebra is simple, and the group will be simple also. In particular, he recalls what is the Cartan-Killing form. So he uses the, what notation does he use? Okay, he uses this parenthesis. So psi, eta, G. So this is the Cartan-Killing form. This is the trace of the adjoint of psi, adjoint times adjoint composed with adjoint of eta. We know this is very important. Let me briefly say why it is important. This is the Cartan-Killing form. Because we can say that G is semi-simple if and only if Cartan-Killing is non-degenerate, and G semi-simple is sum of simple. So really, the non-degeneracy of the Cartan-Killing form is very important because, and then it's is used all the time in the classification. He now, in half a page, summarizes the classification. And I take the liberty of recalling this because maybe not everyone is so fresh with this classification. I don't know. What do we do? Would you like to see it again briefly? Yes? The audience? Francesca is not. Yes. I'm sorry because it's kind of a loss of time because we're supposed to know this very well, but maybe we don't remember. So, what is the key of the classification? No, because let me tell you, in our course, we classify the simple Lie algebras through. Okay, what is the key of the? Because he uses parts of it. So there's simple Lie algebra. So I take G, and then H is a Cartan subalgebra. Okay. I forgot to say important thing. I say this hypothesis is very important because to each simple Lie algebra there is one and only one simply connected group corresponding to it. So there is a correspondence between simple, this before we start, Lie algebras and simply connected Lie groups. Okay? In general, one can ask what are all the groups connected that have G as their Lie algebra. Okay? So there could be more than one having the same Lie algebra. Remember that the Lie algebra is the tangent space of the identity. So for example, if the group is not connected, already you imagine that, there is the connected part will have the same tangent space. So its uniqueness is not granted, okay? But so what are the, but we already assume connected, because if it's not connected, many problems happen. But I suppose it is connected. What are all the groups corresponding to G? This will be the quotients of G by its center. Okay. But once we take the simply connected one, see, you remember is the universal cover, is the one that lays above, then you cannot go above that. So it is somehow the most general possible, and then once you get to that, it will be the universal cover of all the groups having this as the algebra. But the author, I think the author restricts himself to consider simply connected because he wants to get away, saying, okay, there is always one associated, so I have this correspondence. Then if it is another group, it's just a quotient, so I will reason when I need for this quotient. So what I'm trying to say is that taking the simply connected allows you to pass from group to algebra more easily, because there is this one-to-one correspondence. But for the moment, it doesn't mention anything. Okay, so let us go now to the case of the Lie algebra only. So we have a simple Lie algebra. We fix a Cartan subalgebra. I remind you that Cartan subalgebra is a maximal abelian subalgebra of G consisting all of semi-simple elements. And it's not unique. All of these subalgebra are conjugate by elements of the group G. Now you may worry, which group? But say the simply connected. In reality, you don't need a simply connected, but it doesn't matter. You can ask for less, but for sure the simply connected we conjugate them. So we take this Cartan subalgebra, and through this root decomposition, we can write the G as H plus the sum of the root spaces. Let me remind you what the root space is the set of all x in G that transform under the adjoint action, so ADH x, which is nothing but hx. In fact, this h goes before and not after. No, it says before. So the x minus 1 was after, but okay. Is the alpha hx. So the G alphas are the root spaces. They transform like this. So they are the eigenspaces for the adjoint action. So these alpha h are the eigenvectors, except that this eigenvector, you know, h is a Cartan subalgebra, abelian diagonalizable. So since it is abelian, it can be diagonalized simultaneously. So one can always think, we are over C, I forget. We can always think of h as diagonal. And for this reason, this will be the diagonal elements with respect to the adjoint action. And of course, this will change according to how h changes. Now, this is the composition, and we have many properties of this G alpha. Certainly, the dimension of G alpha is 1. This costs some effort. If you take the bracket of G alpha and G beta, this is in G alpha plus beta. This is no effort instead. And then there is a, for each root alpha, there is a friend minus alpha. So the only, okay, if you fix a root, the only multiple of the roots belonging to delta, delta is the set of the roots. So delta, but that's right. How does it call the roots? Doesn't call them delta, it calls it phi. Okay, sorry, let's call it. So this phi is the root system is all consists of all the alpha going from H to C, which are non-zero. And this is a finite number of them because there's a finite number of eigenvalues. This is a finite set. Now, for each root alpha, the only multiples belonging to this phi is plus alpha minus alpha. And if you take, so there exists H alpha in H, and then X alpha and G alpha, X minus alpha and G minus alpha, that form an SL2 for each root. And this is this SL2 is very important. We will use it. We will exploit this property quite thoroughly. So this root system will have some property making it an abstract root system. So, by the adjoint action, I have created this root system consisting of all the alpha in H star that are the eigenvalues. This root system has certain properties. First of all, it's finite, but let me write the properties because he writes them and we have to remember them. Okay, So we associate to a simple Lie algebra uniquely a root system, abstract. So from G corresponds uniquely to this phi. So it's so it's an abstract root system, which means that first of all, is a finite set, and the span is equal to a certain real vector space. Oh no, right, I don't want to see what that is. A certain real vector space. And then second property, if alpha belongs to phi, K alpha belongs to phi if and only if K is equal to plus or minus 1. And then third thing, we have for each alpha we have a reflection defined as beta minus 2 times, I explain later what that is. He doesn't write what this is. I can't believe it. He doesn't write. How are you supposed to? No, he writes it, okay. Beta, alpha. So what is this in our situation? See, because what is this scalar product? So this is a scalar product in the abstract root system. What is a scalar product in this environment? So there is the Cartan-Killing form, allows us to identify G with G star. So this is a non-degenerate product. It's also non-degenerate if you restrict it to H. This is non-obvious because if you have a non-degenerate product, non-degenerate bilinear form and you restrict it, maybe it's degenerate, but this is not. Once you you identify H and H star, through this, you can transfer the product, the Cartan killing from here to here. Okay. So this will be the Cartan killing form restricted to H star, thanks to this identification. And then last property is that this belongs to phi. Last property is this is an integer. This is okay. Okay, so this is so one can prove that from a simple algebra you get this phi that has all of these properties and vice versa. If you have abstract rule system, we haven't done it in the course. You can go back to the simple algebra. Then one has to take a further step that allows us to associate abstract root system to Cartan matrix. Okay, so how do you do this? This is a further step. So first of all, you have your phi. Now the problem is not anymore a problem of Lie algebras, because we moved from simple algebra to abstract system with a one-to-one correspondence. Then we want to go from abstract system to Cartan matrix with one-to-one correspondence. Then one classify Cartan matrices. That is through Dayton diagrams. So in order to make this step to abstract system to Cartan matrix, think about this phi. Now phi that I draw is an extremely simple one. It is the for A2. A2 is SL3C, which is a simple algebra. Okay, so what I do, I take what is called the polarization, what he calls polarization. So you take just one hyperplane in the vector space R, VR. This is the hyperplane, avoiding those hyperplanes that are orthogonal to the roots. And you call what is in this part, you call phi plus. And what is called the other part phi minus. And there is a theorem saying that there exists a base for a basis for VR. So exists basis in phi for VR, so that phi plus consists of all this, none of all, consists of m alpha I, so basis say alpha 1, alpha r elements, where the mi are all positive and integral. So I can write all the elements which are finite and finitely many in phi plus as integral sum with coefficients all positives of the element of the basis. And the elements of phi minus, which are on the other side, will be written with coefficients that are all negative. This is like a cost effort. It's not obvious that this basis exists. In fact, it doesn't look obvious at all. Okay, once you've done this, you realize that it's enough the knowledge of the basis to reconstruct the root system. Again, this is not obvious. And you define the Cartan matrix is a matrix with entries that are this 2 alpha I, alpha j, alpha I, alpha I. Okay, so this is the Cartan matrix. that you uniquely associate. Well, you don't uniquely associate because you have to make a choice. You have to choose a basis for the root system, but this choice is immaterial. If you choose different bases, you'll find the same Cartan matrix. Again, this is non-obvious. And again, it has some properties that uniquely define. Okay, so let's write the definition of Cartan matrix. Definition of Cartan matrix, as we did for the root system, okay? Because, so we pass from simply algebra to after root system, they have to have their own existence. They don't come just from this. And same for Cartan matrix. So Cartan matrix exists. By definition, what are they? Then we associate, right? Because before you want to associate, you need to define. So, first of all, entries are all integers, and the diagonal entries are equal to 2, clearly, because one diagonal is 2. And I don't like what he writes. He writes more than is needed, so I ignore. I don't like his definition of Cartan matrix. Okay, certainly this is I really hate it. I will come back with a book writing the correct definition. So what you want is, so this matrix will not be symmetric, but it certainly will be that Aij same sign as AJI. And when it is 0, both are 0. Okay? So it's 0 if and only if Aij equal AJI equals 0. Okay? And then there is a restriction. It doesn't say it here, but no, it says it. Okay, I'm happy. The third property is that Aij, AJI is between 0 and 3. Now, I think that 3 is possible. I don't remember it, but I think 3 is possible. It doesn't say it's possible, but I think it is. And it happens for the G2 system. I don't know. I have to check this. It says less. I will check this. Okay. And then there are Dinkin diagrams. I refuse to say what the Dinkin diagram is. It's not so important for now. And one classifies Dinkin diagrams.
It could be 3, no?
I think so. It doesn't say. It says less. I don't know.
That's the Dinkin diagram with 2.
Yes, the G2. In fact, I think I know, but if one writes different, I don't know. Okay, I reviewed this because I wanted to give an effective way, which we have not done in the class, from going to here directly without root system. Okay. So if you have a Cartan matrix, how do you find Lie algebra with that? It's Cartan matrix. Okay, it's an interesting question. And here's a typo.